Okay. Hello, everybody. I think this should be live now. I've gotten a couple errors from YouTube in the past few minutes, so I'm not entirely sure. But like I said, I believe that this is up and running now, so hopefully that's true. Let me just get my information for this thing. This did not change its IP, it looks like. So, I don't like the fact that that changed its fingerprint, but I guess I can live with that. Password again. Really should set up keys for all this, but size this one, size this one, and while we're at it, we can do a bind H focus left. Bind L, focus right. So, I think we should be good. I think everything's good for the stream. So... Although it looks like the chat may be broken. I'm getting that little red line, which I believe means that it's not getting the proper responses that it expects, so hopefully it works. In any case, let's see here. Tonight's stream is going to be continuing the CPU errata stuff from Monday. So if you missed that, did I post links already? I did not already post links. So on Monday, we took a look at this CPU errata stuff from Intel. Basically, the whole story is that, let me just copy and paste these real quick. Back in January, there were apparently a series of OCaml bugs that somebody was running into, which essentially, here, we can actually pull these up here and demonstrate them real quick. I don't have to just talk about this. So, this right here is this OCaml bug, which essentially they added some stuff. They switched to a new version of the OCaml runtime, and they started getting seg faults and all sorts of compilation problems. They couldn't figure out why. So after a week or two of working on it on the OCaml side, it ended up getting passed off to Intel. It ended up being investigated at Intel for some amount of time. And then eventually, I'll refresh this real quick. Eventually, it ended up getting patched. So back in May, like late May, Intel released a firmware update that supposedly fixed this issue. Everything that I've seen seems to indicate that it is in fact fixed. But the catch there is that while it is fixed, it, sorry, I'm checking this real quick. While it's fixed, the indication is that it's actually a little bit more serious of a problem than just affecting the OCaml stuff. So, I did that again. I keep doing that when I want to move these around. So this right here is from the Debian list where they took a look at the Errata stuff, and they came to, and according to the Errata, where is it in here? So we've got this Errata here that there are several versions of the Intel processors, specifically some Skylakes and Kaby Lake processors, where under complex microarchitectural conditions, short loops of less than 64 instructions that use AH, BH, CH, or DH registers, as well as their corresponding wider registers, may cause unpredictable system behavior. This can only happen when both logical processors on the same physical processor are active. So, what does that mean? Well, what that means is that we should be able to write some code, get it all working, and in theory, I would expect to see similar problems to what the OCaml people were seeing in just any code we write. So we took a swing at trying to do that on Monday. We wrote some C that looked like it compiled to the right stuff. Like, everything seemed to indicate that compiling it got us the right opcodes. We were able to try and disassemble them, and it looked more or less like it was working. However, it wasn't. We ran it, actually ran it for quite a while, and we never ended up having any problems. Which leaves us in a little bit of an awkward spot, right? That the processor I'm running on should be vulnerable to this. We haven't updated the microcode on it, and yet it's not having a problem. So what do we do now? Well, the plan for tonight is we're going to go back and fix a lot of that stuff up. So there's a couple of things I wasn't quite happy with about the code we were running last time. Specifically, there were some issues with how we were getting into it. Like, we're writing a whole bunch of C to run assembly. So we're going to go through and we're going to fix that first. We're going to clean things up a little bit, and we're going to get it all running. Now, I'm not sure if that's going to be sufficient. The next stage is in the OCaml stuff. There is some disassembly of what they generated that they believe was triggering it. So we're going to take a look at that a little bit. We're going to try and emulate as much of that as possible. And hopefully that gets us there. If it doesn't, unfortunately, I'm not quite sure where to go from there. I've already tried to get a hold of some of the OCaml developers who were involved in the bug report. But at least, so I sent an email out yesterday, but at least so far I have yet to get a response. So hopefully we're able to get all of this to work on our own tonight, but we'll see where it leads us. But before we get started, there are a couple things that are new. Basically, if you are in the chat right now and watching this live as opposed to recording, we hit 1,000 subscribers today, thanks to Ginvale talking about the stream on his stream this afternoon. And the end result of that is that a couple of new options opened up for YouTube, for the YouTube streaming stuff. They gate a whole bunch of stuff behind certain subscriber counts. And at 1,000 subscribers, there's now the option, and if you look in the chat, it's a little thing that looks like a $sign there, which essentially means if you want to, you can send me money. You click the button, they're going to ask you for some amount of money and somehow to pay for it. I don't understand how it works. And it will send the dollars to me, or euros, or whatever your local currency is. There's also an option for paid content. I'm not sure how I'm going to use that yet. I think the right answer may be something in line with how Dan Carlin does the hardcore history stuff. Basically that the streams will always be free. The recordings will stay free for some amount of time, but at some point, I'm going to collect them all up, package them together, do a little bit of editing to make them flow a little bit better. And then after that point, it would cost some small amount of money if you wanted to watch the old recordings. So like at this point, go back, fix up the PDF crack series, and if you wanted to watch that, then it would be $1 or $2. So I think that's the plan there. I'm not sure. It's going to take quite a bit of time, and at least for the next several weeks, I'm not going to have that. But we'll see. At least that's my thoughts on it. We'll see where it ends up, though. And it looks like this chat still is not updating right. It looks like it keeps crashing on me. The little in-stream chat. That's unfortunate. Let me see here. So if I go and I do this, and I'm going to hit that real quick. Does that work? Hopefully this fixes things. We'll see. Nope. I still get the little line. That's really unfortunate. So I'm assuming that line means that the current chat is what I'm looking for here, non-updating. I do have the actual chat open in a second window, so I will catch it, but it means that if you're watching this in the stream recording, the chat may be a little bit lagged. Sorry. So let's get started here. If we come in here, projects, this right here is what we had last week, and just to reference this real quick, we still have a swap file apparently. That's fine. But we had this C code we wrote to basically go in. We're going to start a couple threads. So we're going to start up 2 different sets of threads, one of which is going to be in a loop. And this code, when compiled down, uses the BH register, I think, and the BX registers. And the thought here was that if we did this, then we should end up with what am I thinking? We should end up with somehow getting a crash out of it. But we didn't. So, what now? Well, the first step here is I was awful and did not set up any sort of version control. So I did all this work last time and we never did any version control for it. I'm just going to do this now, get it set up, put a commit for it, because I'd like to be more in the habit of that. Like, it definitely seems like a good idea to be relatively regularly committing this stuff. Git add test.c, git commit. Ooh, that seems fine. Git config global user.email sam@sam.com, sure. And git config global user.name sam. Oh no, this is awful. I'm using nano. I need to fix that too. But end of Monday stream. Exit. Yes. What is it? Git config -- global editor? sys.editor? Oh, there we go. Git commit. I think that's right? Git change editor. Core.editor is what I want. Core.editor. There we go. So I think that should be what I want. So we have all this. So the first step here is we're going to rewrite a bunch of this code. And let's rm that, test rm that, We can get rid of this. We have this right here. And let's get rid of the screen log. We don't need that either. So this is a little bit cleaner now. The first thing we're going to do is we're going to make a makefile for this. And I'm going to have to look up the rights index to use a makefile. Because makefiles are always the kind of thing that you set them up once and then forever forget how to do them properly. So I want to have a test, and this is test.c gcc-o test. I want a test.c in here, and we need a -p thread. I think that should work. So if we come in here, make this. Yep, that works fine. So we have a simple makefile now. We're gonna git add makefile, git commit now with makefile. So that's the easy part, right? We've set up this real quick to be a real project instead of just some super hacky, awful thing. Now what? Now what we want to do is we're going to set up threads.asm. And this is going to be sorry, I'm blanking on the word here. This is going to be a assembly file so that we're going to be able to specify each of these threads separately without having to worry about all of the stupid stuff here. We're going to be able to say, rather than dealing with how is GCC going to optimize to create this specific set of opcodes, we're going to ignore all of that. We're just going to write the assembly ourselves. We're going to link it all together, and that's it. It should be pretty straightforward, and it should just work. So how do we do that? Well, let's start by we're going to set up an extern, which is puts. We're going to have a global, which is thread1, and that's just going to do really simply here, move RDI start string, and then set auto indent. Does that work? Yeah, that works. Call puts ret. That's it. Oh, and we want to do a start st, which is a db, which is thread1 started, comma oxa, comma 0. This is now going to make the string there that we can use. So if this all works the way that it should, dash elf elf64 test this is threads.asm. Now, git install nasm. And that should give us a threads.o, which we would then be able to link in to our C. So we're going to come in here. We're going to edit this right here. And we're going to do extern void star thread1 like that. So we edit our makefile. So now we're not going to just have our what's the right syntax for this? I want to do C files. Right, so I did that, which means that I should be able to come in here and have C files like this. And let's just verify that real quick before we get too far along. CD projects, Skylake, make. It is up to date. It is most certainly not up to date. Oh, C files is equal to test.c. Right, that makes sense. So in addition to doing that, we need to run that NASM. So we're going to do NASM -elf64. So this is creating that threads.o because we, I mean, that's what we want. And then we want to do threads.o. You know what? We'll just do it this way. Threads.o, like that. Threads.o. We're going to be a little bit messy with this. That's fine. And we want to specify threads.o. Sorry, this is threads.asm, not .o. So what this does, right, is we see it ran the NASM. Oh no. That's unfortunate. Crap. I have broken everything. Resize that to 80. Okay, that looks better. So our makefile, right? We set it up. It will first run the NASM -elf64 threads.asm, and it will run that if either the C files we have or the threads or both have changed. Then we're going to use GCC to create a test binary, linking in the threads.o that NASM put out, and compiling all of the C files we have with the pthread library. So, assuming all of this works, we should be able to come in here, do .test. Let's just change this real quick. So, CD projects, Skylake. Projects scale 1. There we go. Vim test.c. So if we just have this to, instead of doing that, we're just going to return. Make. That's fine. Run it. It does basically what we expected it to, right? So when our assembly was set up to call thread 1, yeah, so Ryan in the chat is saying that I should be using Clang and CMake. That's probably a good recommendation. But I actually know how to use GCC and Make kind of well. CMake I don't like using at all. I've used it a couple times. It is way more complicated than I want to deal with most of the time. This kind of just works. So where were we? Let's actually drag this over here so I can see it on the side of my vision a little bit better. I'm reordering the windows that are off screen because I'm not going to be able to see the chat moving quite as well where it is. So we have this now. Basically, instead of having a... where are we? Oh, there we are. Instead of having two threads that are written in C, we're going to put starting everything. We're going to get rid of this too. We're going to write both of our threads in assembly directly, because that way we're going to be able to fully control exactly what they're doing. And just in case you're curious, the reason why I'm calling puts here before we start the threads is because I want to make sure that it gets initialized properly. Because if it doesn't, and it instead, what's what I'm looking for? If it doesn't get like libc and the way that the standard IO works is kind of a pain in the ass. Like it does a lot of initialization the first time it gets called. I want to make sure that it gets linked in properly and that everything just works. So I'm just going to print out a string here. That way in each of the threads, the linker will know where to find them. The stuff that NASM puts out will know that, oh, there's puts out there someplace. We'll just call into wherever that is. Then the linker will figure it out from there when we actually link everything together. At least that's the plan. Where are we? We have both these. We're going to write thread 2. So we're keeping this all very simple. I believe here. Yeah. So we have our global thread 1. We're going to have a global thread 2. Thread 2. And we're going to do the exact same thing again. RDI start string 2. Call puts ret. Start st2 /1. We're going to replace that. Make. See, super straightforward. We start everything, we start up all these threads. Each of our threads is running assembly now, as opposed to some sort of compiled C stuff. So we're actually going to do this. And we're going to, since we've made some nice changes here, threads.assembly, or git add threads.asm, git add test.c, and git add makefile. Now using assembly for threads. I should spell that properly. Not that it matters too much. So we have all that now. Now what? So, if we come back over here, I'm going to juggle all of these windows again. If we come back over here, we remember that we need a complex, well, this complex microarchitectural conditions is quite possibly the most concerning part about this, because that could mean basically anything. That we need like we need to set an XMM register to be certain values, or one of like our, there's so many things that might mean that I cannot guess from this 2 sentences worth of text. So we're going to ignore this for now, and hopefully come across whatever it is it's supposed to be without having to deal with that. But what we're going to do is we're going to set up AH and the RAX register. We're going to use both of them in a loop that's going to be only a few instructions long. We're going to set that up for thread 1. Then we're going to use thread 2 in such a way that it's also going to loop, and it will hopefully do things that work out well. But we'll see. Where is this? There we go. Oh, there we go. Yes, that worked. And I don't understand why this little overlay keeps crashing on me. Like, it is constantly crashing, which is that little red line you're seeing in the chat if you're looking at it on the stream. I'll have to keep remembering to hit it again. Where are we? So we need to write that now. So we're going to come in here. We're going to have loop 1, jump loop 1. So this is our loop. And we're just going to be super simple about this, right? We're going to AND AH with some value. So we're just going to AND it with 1. Or let's clear it out, right? Let's clear out AH. That makes a lot of sense. Because that'll just work, right? I'm trying to think about this real quick. So ideally what we're going to do is we're going to have... Actually, we're starting up a whole bunch of thread 2s. I should do this properly. So thread 2 is where we want to do this because, again, ideally what we're going to end up with is a situation where oh, I'm sorry. I've gone all this time now and forgot to switch screens. So thread 2, we're going to start up a whole bunch of different copies of this. And ideally, that's going to let us... I'm sorry, I'm blanking here. Words are hard. When we start up a whole bunch of thread 2s, those are all going to fight each other, essentially, which will hopefully make it so that we're more likely to run into this error condition. And just because we aren't... and I hate that I have to keep manually refreshing this chat. But it should be up now. But yeah, hopefully by doing it all in thread 2, it shouldn't matter how the threads end up on which cores. We'll have a whole bunch running thread 2 and one running thread 1. The end result being that thread 1 will hopefully be the right thing. And that thread 1 will cause a problem is the hope here. So let's actually write that. So loop 2, jump loop 2. Now, we want to do a little bit more than that, too. If we do this the easy way, geez, I'm having a terrible time right now putting things in words properly. What we'd like to have is... So in this loop... So in loop 2, we want to change both BH. So this changes BH. We're going to AND it with 0. So BH is an AH. I would like to do a move RBX RAX. So we're going to save off whatever's in RAX. And RAX is actually going to be what puts returns. But we're going to go a little bit farther here. Move RDI OX 1000. We're going to create a page here. Extern malloc. Hopefully this all works. Do I have hyper-threading turned on? Yes, I do have hyper-threading turned on. Cat proc/CPU info. So I have 7 processors and I have 4 cores. So yes, hyper-threading is on. I also have the proper microcode version in that this is a version that should be old enough that is vulnerable, at least according to the Debian report, that it is fixed in B9 and BA, and we're all the way back on 84. At least that's what Debian says. I assume they know way more about how the microcode stuff works than I do. I only have the very basic idea of how that stuff works, because how microcode actually works is kind of magic. So we're going to call malloc here, just to get a new... I want to save this off, and I believe I can save this to R10 and not have problems. Move Rex R10, because I think R10 is one of the x64 registers. So yes, it might not show up particularly well on the stream, but it is, in fact, a 8.4, not a B4, so we should be on the right version. So we have that working. We have this set up. So what this means is that RAX should be unique to each thread. We're then going to AND this with 0. We're going to write to it. So I want to do a move RAX sure, we're going to do that. And then we're going to, at the start of our loop, do a move rax RBX. So Ryan was asking in the chat, what do I think the unpredictable behavior is? So according to the OCaml stuff, we didn't actually go through this very much last week, so we can do that real quick. If I can figure out where I ended up putting that. Here we go. So according to the OCaml stuff, among other things, they got seg faults from it. They also got corrupted data. One of the things that's really interesting in here that I saw was, where is this thing? I don't want any of this, or that. No. So there's a comment in here someplace where one of the OCaml developers mentioned that he was running code on a like entire server range of Skylake processors. So they're all supposedly vulnerable, but it wasn't crashing. What was happening was the data, they were doing some sort of complex like machine learning analysis stuff, and the data was coming back wrong. So if you read through all of this, basically the conclusion they came to was that, where is it? So in the garbage collector, there is a slice, or wrap slice, I think. Where is it? Slice. Sweep slice. That this sweep slice uses the AH register and then immediately uses the REX register. And at least the supposition here is that when the garbage collection triggers in a condition that is true to the Intel Errata report, the theory is that that is causing memory corruption somehow. It's changing some values someplace on another thread. At least that's what it looks like. So what I'm hoping for, and I've got a couple guesses here. Like I mentioned on Twitter, I talked to Brandon Falk about this a little bit yesterday, and like we chatted about it, and the conclusion we came to is that what is probably happening is that somehow there's some microcode that's running for some reason, and using the AH register, apparently that adds a single micro op to the instruction that's using it in order to recombine it back into the full registers. So the supposition is that somehow that isn't restoring a temporary register properly, and the end result is that, so we AND AH with 0 in one thread. The thought here is that that is going to cause AH to become 0 in the other thread. Now, I don't know if that's true or not. That is us completely spitballing. Like, I have nothing to prove that that's what's happening. I just kind of, like, that sounds at least somewhat plausible. So yeah. Let me see here. Actually, I want to do one more thing before I do this. So we're setting all this up. And I also want to do init2. That should be a 2. Compare AH to 0. Jump equal. So if AH is 0, we want to jump to init2. Basically, I want this to keep allocating memory until AH is 0. And the reason for that is because we should be able to say in loop 2, when we set this up right now, compare racks, trying to think of the best way to do this. So we've just modified some memory here. It's entirely possible this is actually going to cause a seg fault to begin with, which I don't exactly like. Sounds like the other thread should have a test against AH. Right. Oh, I should update the chat. That is my expectation. I'm just trying to add in as much here as possible. Because I also want to control for... Yeah, you're right. Let's not worry about that yet. We can potentially come back and do this later. So we've set up this. We're allocating a buffer. We're going to print out our start string. We're then going to try and write to it. I'm a little bit concerned about this part right here, right? So we are writing to this register, but we've changed it. I'm trying to think of what the best way to handle this is. Oh. Duh. So the AH register is going to be these 2 bits right here, right? Oh god, what did I do? Ah, there we go. So it's going to be that byte right there. So when we call malloc, we're going to call it with a big buffer. So it doesn't actually matter where we are in it. Like, we should be able to say that regardless of where we end up in this buffer, it's going to be valid, and it will be inside of our space. So we've allocated enough space that we can safely say that regardless of where that puts us, we're going to be valid. Let me make sure this actually works out, right? So let's say we have malloc return, you know, the 20,000 hex there. Then we're going to add right? And then when we AND that with 0, we will be someplace within the memory that we allocated. Let's add a comment so that actually makes sense. This way, racks and ox fffff, many f's, 0, 0, 2 more f's, is in buffer, right? Like, this way we know that this will be in our buffer. So we do that, we print out our starting string, we save off, we set this back up, so we're going to put R10 in RAX, we're going to put RAX in RBX. It's not guaranteed. Why do you say that it's not going to guarantee to do that? As long as it is returning 20,000 continuous bytes, I believe it will. Because I think the way the math works out there is that... Yeah, okay. It looks like the chat is a little bit farther behind than I would like it to be, too. But yeah, I think that should work out the right way. So we have that. We set that up. We should be able to write into it. We then jump back to the beginning. That should just work. And then up here, we're going to do a move rax ox 41 41 41 41. Actually, 8 append 41. Zoop. And we also want to do move rbx rax. So loop 1 is going to be super simple. We're going to compare rax rbx. What am I doing here? Jump not equal to error. And error is going to be right here. That's going to be an int 3. Yep, there we go. Right, so the reason we want an int 3 is because that's going to give us a core dump, which should, in theory, be exactly what we're looking for. Like, we should be able to use that core dump and use that to get where we want to be. I think that works now, right? I'm always shocked that I wrote that much assembly and it just actually compiled. Before we do that, 3. We want to call... We're going to call malloc here, just to make sure that it is all initialized. That works. Well, it kind of works, right? It ends up doing the thing that we expect it to do. It doesn't end up crashing like we want it to do. And I also want to do, what is it? Set... task set? Is this it? Yeah, so task set will let me do... I want to set the mask to 1 and run test. And supposedly what this does is this means that all of these will run on the same core. At least if all of this works the way that I think it works, this should give us our int 3. But it's not. But it is not. So, let's run this and make sure that all of this works the way that I think it should be working. So we're going to break on a thread 2. We are in thread 2. Set disassembly flavor intel x/20i rip. So does this look proper? We call puts, we then call malloc. This is not correct at all. This is not even close to being correct. Right. It restricts it to a single logical processor. Oh, that's interesting. I did not realize that it would work that way. Supposedly I want task set 3. Okay, I will definitely fix that. But this code is not what I told it to write at all. Like, what I want this to be doing is I want this to run... Okay, am I crazy here? Like, that is not even close to... Oh. Make. Seriously? Okay, we're gonna bash SSH back into this thing. We're compiling it as a 64 process. download cd into binary ninja. We're going to start up our binary ninja. Oh, I should start as X server. That would help too. Come on. Sorry, I know you can't see any of this. Due to some stupid reasons, I have to do this in a different terminal. We have our binary ninja here. I want to move this down so we can see it properly. We're going to refresh this again. So we're going to open this file. We want to open test. So we have main. We're mallocing 1, we're printing starting everything. We then create a thread. So this should be thread 1. What? Why on earth did NASM... Okay. That looks a lot better. Well, I mean, not better, but I can live with it at least. Operation size not specified. Oh, did I forget to save? Set new. That's the right line. Move keyword that. Okay, so this is running again. We're going to reload this. We will discard it. We're going to reload it. Yeah, sorry about that. I did not show my changes to the assembly there, but coming in here, let's make this a thread. This looks like what I wanted to have, right? We're going to jump back over here. That looks reasonably correct. Although it's not, yeah. We set up REX, we set up RBX. If they are different, we're going to error out. We're going to int 3. Otherwise, we're going to loop. And then this right here should be our thread 2, which is doing, we malloc our buffer, we add to it, to index into it. We then set that up in R10, just print out our string, we save all that off, and then in this loop, we do everything we wanted. So, if we come back over here, we can see it still hasn't crashed. But, okay, so according to Gubbanite, we need to check the sibling value from proc CPU info to find sibling logical CPU, and then make the bitmask the pair of those. So cat proc CPU info. So how do I do that? So I have processor 7, which has stuff. Siblings are 8. Well, let's just, yeah. So for processor 6, siblings are 8. So we have CPU, we have core ID 2 and CPU cores 4. So it looks like, right, that processor 4 has core ID 0, and processor 0 is also core ID 0. So if I'm reading this properly, I believe that that means we want processors 0 and 4 to be our mask. So that would be OB10001. Right, so we want the 0 on. We want processors 1, 2, and 3, or cores 1, 2, and 3 off, and then 4. Oh, that. So I think our mask should be 17. But you say that LSCPU. What is LSCPU? Oh, what is LSCPU? Man, LSCPU. Display information about the CPU architecture. Okay. Not quite sure how to interpret this. Let's give this a try real quick. So task set 17 test. I also don't know how to validate that this is working the way that I think it should be working. I mean, in theory though, right? If we just don't specify this, we're starting up 8 threads, which are thread 2, right? 1, 2, 3, 4, 5, 6. 6 thread 2s? That's not what I want. Oh. We're going to have TID 9, TID 8. S7/8. 7/9. And that should work, right? So this will start up 8 copies of thread 2. So regardless of which core thread 1 ends up on, it should share itself with thread 2. I think that's how that works, right? Git status, git add threads.asm. We should be running the tight loop on all cores 1 checker. Right, so regardless of which core thread 1 ends up on, it should be sharing that with at least one thread 2, because thread 2 should, I mean, assuming that it gets distributed evenly across all of them, running on each core. So ideally, what I would expect to be seeing here is sooner or later, thread 2, or thread 1, causing an int3 and crashing. But it's not. Oh, but it's not. This is the real hard part about doing all of this, right? That we have, you know, what amounts to a line and a half of text. Not even that. Like we've got a line of text about what exactly the bug is, and really not much more than that. Like all we really have is that we want a short loop of less than 64 instructions. Ours is like 3. That uses AH and RAX. And because of how this is set up, it is almost certain that we will end up in a situation where thread 1 and thread 1 and a thread 2 will end up on the same core. It shouldn't be possible for that not to happen. But it is. Or we're not hitting the right conditions. So this is the other part of this. So in the I don't want you to actually download this. Here, I'm gonna switch this off real quick and make this so I can actually read it. Show this in folder. What can I open you with? Sure, Sublime will work. We'll come back to this. So this is the opt.s, and opt.s is the, so Joris, I don't know who Joris is, he's one of the developers who was working on this, attached opt.patch, a diff on top of OCaml 403, which is enough to trigger the bug on top of O1. Unopt.s is the assembly generated by GCC for the garbage collector with O1 as the optimizations, and opt.s is the assembly generated by GCC for major, the garbage collector, with opt.patch. So opt.s ends up generating a binary that triggers this issue. So what is this? To start with, this is AT&T syntax assembly. It's a bunch of it. I think it's a couple thousand lines, or it's actually quite a bit more than that, isn't it? It is just shy of 6,000 lines of assembly. Yay. But we know that, what is it? Wrap slice. No. Slice wrap? What is it called? Sweep slice. So supposedly, sweep slice is where they believe they're triggering this errata. And if we look through this, sweep slice doesn't seem particularly complicated. Although, let me actually look this up before we go too much further. This might be easier. So, compile.s. What is a .s? Oh. So supposedly, I should be able to take this .s, and I should be able to pass it to GCC and get a binary out of it. Let's see if that actually works. What is this? So Ryan has posted a link to this. We could not find the page. Okay. Oh, hey, this is from Joris. Look at that. This is so convenient. Oh, hey, the chat didn't crash again. That's cool. This is from one of the developers talking about it. So our story starts in late 2016. Yeah, tracking down the crashes. Oh man, this is exactly what I would have liked to have had. That is awesome. Yeah, this part right here is crazy. I cannot imagine going through debugging this. They apparently dug through, like, compiling this, trying to fix all of the potentially undefined behavior in a massive code base like OCaml, just in case that might have been it. So they're talking about all this. They're talking about how it is O2. We convinced ourselves that disabling hyperthreading could affect cache pressure and unfold some undefined behaviors. It would also determine the non-determinism. yeah, 50 C files where with O1 it doesn't happen, with O2 it does. They then do like a bisection of their entire code base to try and figure out which of those files is causing the problems. The sweep slice function is the last pass of a normal major collection cycle. It's responsible for scanning all blocks in the major heap and reclaiming unreachable blocks to the list of unallocated space. Okay. When the block is reachable, the color describing the reachability status of the block is reset. Okay. Don't really care about the internals of their garbage collector. Okay, like they're talking about like going through some nightmare issues trying to fix this. They are now certain that it's a CPU bug. Yeah. So this is great. Fortunately, it does not look like it actually gives us what we want. Like, yeah, see, this is in fact the part that I was guessing would be that. So what all are they doing in here? They are writing a chunk to racks. They then read something out of it. So this is their like header stuff. They're going to like they're using it all over the place. And so we're anding it. Oh, where is this? Here is what I assume is that tight loop, right? They're going to. Oh, they're doing the other direction. Okay, I need to fix that. So they are anding age with a constant. Then, oh, sorry, you guys can't see that yet. So they're anding age with a constant, 255. Then they're going to move it into a memory address specified in RBX. The code we're using right now is doing the opposite. We're writing a value into RAX. So, I mean, we can fix that real quick. That shouldn't be too bad. 0? 0. So instead of writing a keyword into that, you know, let's write racks to racks. That should work. Make. We're doing the same thing, right? We're now doing a write of racks into racks. So that should be equivalent to write, like if this is dependent on writing the RBX register into the RAX register after doing an AND, like that should be right. And then they're going to jump back up here and loop through again. What else here could potentially affect this? So it is using rip relative addressing to figure out what racks is in this loop. I don't think that's going to matter, but it might be worth checking. Like it's worth verifying that before we completely roll it out. It is also reading out of that address too. So racks is equal to, or I can't do that. Move racks, keyword racks. So that's now going to read out of it too, because that is what happens up here, right? So we're reading racks out of a memory address specified by racks. And then we're saving it off to a rip relative address. We also test RAX to make sure it's non-zero. Well, so Ryan mentioned in the chat that at least there are no exotic instructions. Having an exotic instruction in here would be amazing because it would tell me exactly what I'm doing wrong. It's great because it means that if we can figure out what is causing this, like if we can figure out how to trigger this, then we can go out and try and figure out what to do in a, like, what does this bug look like in the wild? But if we can't reproduce it at all when we're writing our assembly, like, I'm not quite sure what to go from there. But, so we have this, we're reading from it. Let's test it too. We're gonna set some flags with it. So, test racks. I don't think we need to jump based off of it. So the difference between test and compare, jump not equal, right? We're gonna do an int 3 here too. And we'll change it to jump not 0 so that it's a little less confusing. So we assume that we can't read and write from 0. That seems plausible. And that's lining up with this bit right here. We're writing that out there. We're reading from it again. We're writing it again to memory. We're messing with RBX. I don't think that should matter. We're reading RAX from RBX. Again, I don't think that, like, one memory address should not matter that much. So Anima mentioned in the chat, why am I doing an int 3 as opposed to an int 3 with a space? Because I can't type right. They should not be different. In that int 3 is a special case of a breakpoint instruction. Int space 3, I don't know how NASM handles it, because there are actually two different instructions. There is the CC instruction, that is the OXCC instruction. Oh, here, I'll switch over so you can actually see what I'm typing. So there's the OXCC instruction, which is an int 3 that is a single byte. There is also the interrupt instruction with the argument of 3. I don't actually know which one's which in NASM. Like, they should both do the same thing, though. Int 3 and int 3 are different. Yeah, CDO3 is the opcode for it. So I don't know if NASM is going to be clever and try and optimize it for us. We can actually take a look, though. We have a disassembler here. We can come in here. We can go, which one did you give me? So int space 3 is what we used. And if we come in here, there should be thread, thread 1. And it gives us a int 3. It gives us a CDO3. So yeah, that's what the difference is. If we got rid of the space, it would give us a CC instead of a CDO3. So, yep. Yeah, we'll fix it real quick. I don't think it matters because, like, realistically, the difference shouldn't matter. It should end up doing the same thing. So I'm trying to think of what else could we be failing on. Because we're getting very close, like, we're doing all the same things. The only thing we're doing different. Well, actually, let's switch over again so that you can see what I'm reading. We're going to drag this over here. The only thing that I see here that's different is, one, they're reading and writing from a RIP relative address, which I could see Intel doing in a way that matters. And this is not using RAX. This is saving it off to RDX, but I don't think that should matter. Yeah, the only thing that I can think of that would change in thread 2 is rip relative addressing. NASM rip relative. How do I do this? So I should be able to do... Oh. Okay. So I should be able to just go... Oh, and you can't see this. Sorry. So yes, I am reading and writing with REX, but they are 2. Yes, AT&T syntax is the worst. I wish it would go away. But unfortunately, that's what GCC uses. It's the same reason why everybody absolutely despises trying to write inline assembly for GCC. Like, it's really the worst. Why is this still, like, I don't know why this isn't crashing. Like, the only other, so Ryan mentioned that we're using, where is this? I had this, where is this? Oh no, this is not what I wanted at all. I was looking at this one. That they're using RAX. So they are writing to RAX, but I really, yeah, you know what? Since we're trying to make this as close as possible, let's make that as close as possible. So we're going to write to RBX. Oh. Make test. Whoa! What? No, that can't be right. We haven't even started yet. We're reading from RBX. Yeah, it is definitely on my list of things to do to learn how to use Rust properly. I'm actually planning, I think, to spend like a weekend and learn Rust properly. Or not learn Rust properly, because a weekend is not going to be sufficient, but I'm thinking that it will should be sufficient to get me at least someplace. So I think this is me being awful and not understanding why. Because no fucking what? Oh. This is me being bad. It's because we just, it's because we don't know how to use computers here is the problem. Whoops. That is not working. There we go. So the problem here is I'm apparently terrible and don't know how to use computers. We're testing to make sure that RAX is non-zero, because that was one of the things that they did. They don't care though. We were then reading from RBX, which has not been initialized, and testing that it was non-zero. We then jump only if it's non-zero to loop around. Sorry, everybody. Was not as easy as it looked. That RBX matters. So, now what? I'm not quite sure where to go from here, right? It looks like we're doing everything the same. One thing that was brought up was that complex microarchitectural state is a very concerning line to me, because it is possible that it doesn't just require this one thread. So I have an idea of how to make this thread work. I don't know how to make the other thread work. Like right now, our second thread is just going through this loop, right? It just checks to make sure that REX isn't changing. If it changes, we crash. That's it. Super simple. So now what? What we can do here is we can try and make this more complicated. One of the things that was posited, and this entirely is credited to Falk, is microcode does not trigger on every instruction. Very small, very efficient instructions will not ever use microcode. So, if they're issuing a microcode fix for this, it means that the fix has to be applied to instructions that use microcode. Which means if there's a fix like that, then clearly we need instructions that use microcode. And in thread 1, none of our instructions are going to use microcode. Compare REX RBX is a very efficient instruction that doesn't use microcode. The jump not equal is not going to use microcode. So that loop will never trigger microcode, so it should never apply. Now, I don't know precisely I don't know good ways that I absolutely know will trigger microcode. I have a few ideas. One thing that I think should work, what's the right syntax for this? I want the Intel manual for x86. So I know, oh, it's loading, that the Intel x86 instruction for div is very inefficient. So, and I don't, Intel does not specify what they issue microcode for, so I don't actually know how, wait a minute, is that true? So they don't officially tell us what they've issued microcode for, but we do know that they have microcode patches for certain instructions. So I should be able to come in here, right? If I come in here and I say, so this, if I pull it over here, come on. Oh, sorry. I am trying to move the window on the wrong screen and was confused why it wasn't moving. So this right, no, you need to go back to where you were. All right, I think I've broken everything now. Okay, so this is back where we were. This is the microcode update stuff from Debian. And we can see here, this is their discussion of the most recent set of Errata. So there are undisclosed Errata on desktop, mobile, and server processor modules for everything. Awesome. There is a likely fix for the TSC deadline. Don't know what that is, but so basically what I'm thinking here is if we read through this microcode update stuff, this will tell us what got fixed with microcode, so it should let us know which instructions have to have microcode, right? Unfortunately, so I mean, ideally, I would know how to look at this thing. This right here is the list of microcodes that are updated. I don't know what that means though, and as far as I know, nobody does. There's like a dozen people at Intel who know what this means, and basically nobody else does. So what do we do now? So can we use this information to somehow figure out something which is going to use microcode? And use that to figure out how we can trigger something that's going to use microcode with the assumption that that's going to be something that is likely fixed. Also, now that I've said that, if I come back over here, so this is, of course not. I hate that they give us this and not quite what we want. Why is there not... I have an IP. So what I was thinking here is that, oh, wait. They listed crashes in here. We can just use that to know what the crash is, right? Well, no, we aren't quite that lucky. Because the crashes, while they're right there, they don't just work, right? They didn't tell us what that instruction is. Although... Program terminated with SIG-SEG-V segmentation fault. That doesn't quite tell me what it is. I was really hoping that I'd be able to take a look at this and actually see what they were seg faulting on. I'm curious. We're going to shrink this down a little bit so we can actually see. They have assembly files, but they're for what's causing the loop, not for what is crashing. At least I didn't see ones that were full. So I want to switch to, how do I do this? I want programmer. How do I input hex? I want hex. How do I use it? Oh, here we go. So 1BO. No, this isn't working at all. So what I was thinking here was that this, if this is correct, that they did, when they did this and 252 with AH, what we should, in theory, see then is the faulting addresses, assuming this was simple, faulting on the same, like, it means that the bottom 2 bits of AH are unset. Yeah, so what we're currently doing is we're running, you know what, it doesn't hurt to do that. We can always start up many instances of this. Yep. Yeah, so we've got 4 instances of this running. I have 4 processors. I would think that this should mean that we end up on the same core, but we'll see. It doesn't hurt to try it, right? So, yeah. Do they have comments on these things? They don't have comments on these things. Oh, they're hiring. And they write Rust. Look at that. So I think the situation that we're in right now is we're matching this. We have a short loop with AH and the wide register. It requires both logical processors to be on the same core, which we're on. However, I think what we're missing is this complex set of microarchitectural conditions. And quite honestly, I don't know how to triage that. Because my guess is that this is requiring microarchitectural conditions in the other thread. That we need to get the other thread doing some specific set of things in order for us to get this corruption. Because the guess here is that, so in our code, wrong screen. In our code, we're doing in thread 1, all we're doing is we're making sure this is the same. And it's a very simple, very tight loop. So the thought here, at least, is, well, what if that doesn't do anything? Like, it's entirely possible that is not sufficient to trigger whatever it needs to be in the other thread. But in order for that to get us anywhere, we need to actually figure out what they were doing in the other thread. I really wish we had like a core file here. That would be perfect. Because if we look at this, so this right here is the .s, which is the output from GCC. But this doesn't get us where we want to be, because this doesn't tell us what the IPs are. If we knew what PC was, maybe we could track it down. But this doesn't tell us PC. I don't think any of the other .s's will. The patch won't. The diff won't. If only they did a little bit more with their debugging here. Just need a little bit more information. Because like if I could track, if they had what the instruction it was faulting on was for each of these, that'd tell us a lot, wouldn't it? So one thing that's interesting, I don't know how relevant this is, but if we look at these, this first set of reports here, this and 252 changes. This and 252 does not. This and 252 does not. This and 252 does not change. So 3 out of the 4 of these accesses, if they were modified, just directly modified, by having AH apply to them, it would work. What if we do that real quick? So let's do some memory I/O. So move RDI that we're gonna call malloc, move R10 racks, move keyword R10 racks, and then move racks keyword R10. So now we're going to read from memory every time. I don't know if that's going to change anything. Kill all a.out. Or kill all test. Make. So now this thread is taking just a little bit longer, right? Like we're now hitting memory every time. And I don't know if that's sufficient. I'd hope it was sufficient. But it looks like that is not quite sufficient. Looking at a few of these other crash, oh, I should switch this so you can actually see my other screen. Looking at a few of these, like the cannot access this memory address, that the low 2 bits is not set. See, only they would have given us the full register state, if only. So this is at interp.c, line 292. This caused a seg fault. They tried to read from a pointer of some sort at index 0, and that caused a seg fault. So SP somehow got turned into 0, or a invalid address. corrupted heap information, but I don't know how useful that information is. I do like how Mantis is expanding out the pound 3, that is supposed to be number 3, to be a link to a bug report. This looks like a buffer overrun while walking a large block, but the block is strange as far as I can tell. Why are you doing it this way? This text, like, This looks like nothing like what I want to be reading. This is another one where the low 2 bits is not set. The low 2 bits are set here, though. So, again, my gut feeling here is that we need thread 1 to be doing more. Not quite sure what more, though. Well, we can do a couple other things, too, right? We can do... Oh, and I should switch this over so you can see me. LEA R11 R10 plus OX20. I think that's the right syntax for that. Move RBX R11. Like, we're just adding a little bit more here to hopefully cause more problems. And yet it still does not do anything differently. So let's think this through for a minute. So we know that a microcode update fixed this. We know that then we need to be triggering microcode. I don't know if an LEA is going to do that. So if we come back over here, let's go back down that, line of questioning we were doing. Can this tell us something else that we know is running microcode? I don't think it's that easy, right? So it needs to be something relatively common that is, well, we can always do this, right? We want to make this more common. I want to move R12 OX10. Like, that's a pretty complicated instruction, right? This is where somebody says, no, actually, Intel is able to make this work incredibly quickly because they've, I don't know, pipelining and the black magic that goes into compiler optimizations and processor optimizations. Like, that's probably the most complicated memory access I can think of. Unless we make it all one instruction, right? Let's do that. This is R10 plus R12 times 2. Right. LEA on its own is a simple instruction. However, with the built-in math, I think it has to be at least somewhat complicated. Yeah. Like, my thought there was that at least the LEA was going to make it something complicated enough for it to trigger something. So the floating point is an interesting idea, right? Like, floating point is definitely complicated enough for us to need something with microcode in it. However, if we look at some of these segfaults, all the segfaults look like they're in memory access code, which feels to like, ooh, wait a minute. Maybe we can figure out what this is. So camel interpret. It's not in here. I was hoping that that would be, but so what is this thing doing? So for whatever reason, it's telling us that in this, we end up with a corrupted heap somehow. So what is this doing with REX? And yeah, you guys can see this. What is a CLTQ? I actually have absolutely no idea what a CLTQ is. None of the rest of this looks particularly complicated. They're doing some tests. They are anding it again. Interesting. So now we're going to and AL41. If nothing has changed, that instruction is a no-op. If it has changed, then we might be doing something useful. Or let's actually do this. Right? So by anding 4141 with 4141, we return 4141. So that's what I wanted to do. I wanted to run their code and triage it. The problem is that their bug report is not sufficient. Oh, I'm sorry, I'm not showing you what I was writing. The bug report, I couldn't get to do anything. Like, the bug report is basically, here's some OCaml code that when I have compiled the OCaml state from source with this set of flags, we get a problem sometimes. Which, considering, one, I don't actually know how OCaml works. It's confusing and scary. And the so I played with this a little bit yesterday. Like, I was looking into it, I'm like, you know what, I'll just get OCaml set up, I will get it compiled, I'll run, because they have a .ml file in here. So in the initial bug report, it's basically if you pull down this report.tar.xz, supposedly you can run this right here with OCaml 403, which is compiled with -02. Okay, that makes sense. In order to do that, I need to get the entire OCaml environment building, including OCaml find, which is a pain, and I need to install the extprot library in, or package, or whatever they call them, for OCaml. And I got about as far as I was running into dependency problems in OCaml, and I was like, you know what? I have no idea how to proceed from here. If somebody knows how to actually get that to work, like if somebody knows OCaml well and can make this work, that would be amazing. What I'm hoping for is I've already contacted Who is he? One of the guys in here I tracked down an email for. This ex-Leroy guy. Apparently he, like, is one of the core OCaml developers. So I shot him an email and I was like, hey, it sounds like there is a, like, relatively easy to reproduce version of this. Any chance I can get a copy of it? If we come back up here, this command right here. Like, it's super complicated. It does a lot of things. I don't understand what almost any of them do. I think I'm going to try and get a hold of the Joris guy, too. See if maybe... because I now have a Medium post by him. So it is quite possible that he is much easier to get a hold of now. And maybe I'll be able to get a hold of him and get a way to reproduce this. Because I think that's really the way forward right now. Writing assembly is not reproducing this. Which means there's something more complicated going on. And unfortunately, like, my gut feeling is we need to change thread 1. We need thread 1 to be more complicated, and that our thread 2 is doing basically the right stuff. So I think what I'm going to do at this point is we're probably going to call it an evening now, and we'll reach out to... I'm going to try and reach out to Joris, and maybe if I can track down any of the other developers here. So there's Joris. I wanted to try and get a hold of Shinwell, because he was the one that was actually interfacing with Intel. But I cannot find any contact information for him on the internet. The only thing I can find for him is a GitHub, and I can't figure out how to send a message to somebody on GitHub. Like, I could, like trigger a pull request for one of his repos, but that's the only way I can figure out to get a hold of this guy. So I'm going to see if I can get a hold of Joris too. It's the worst case scenario, right? Like, these guys say, no, we're not going to give you our reproductions. That would be bad. And we're right back where we are now. So I'm sorry that we didn't get... we still don't have a reproduction of this. I'm going to let this run for a while. Like, at the very least, I'll let this sit in the corner and run all night. I figure that can't hurt. But other than that, I think we're going to call it a night for the evening. We've got stuff. We've got stuff that I think should work. And other than getting a hold of one of the OCaml developers, I don't really know where to proceed from here. Hopefully, sometime over the next couple days, I'll be able to get a hold of one of them, and they're going to be able to point me at something I can do to reproduce it, other than figure out how to build all of OCaml from source. Like I said, that is scary and it seems really hard. At least my tries on it took more than half an hour. So, in any case, thanks everybody for coming. A little bit disappointed we didn't get any farther and all the problems with the chat at the beginning. But thanks for showing up. Hopefully this was interesting. Like, hopefully people were able to at least take something away from it. If only the, like, here are relatively easy ways to interface my C code with raw assembly that is not writing the awful inline assembly in GCC. So hopefully at least that's something that people were able to take away and will be able to make use of. But anyway, thanks everybody for coming, and the next stream will be Monday. Next Monday at about the same time, so that's Monday, July 3rd. And while I'm at it, if you're interested in the CTFs, this weekend is Sequencide Quals, which should be a relatively good CTF. I remember playing in it, I think I missed last year, but the year before we played in it, and it was a lot of fun. If I'm remembering the right event, then 2 years ago, it was a lot of fun writing shellcode that was valid UTF Hebrew. I got to spend a few hours on that. It was a lot of fun. But like I said, this weekend is Sequencide Quals. I do recommend giving it a try if you're interested in the CTFs. Other than that, Labyrinth is still ongoing. It's the like long-running CTF by Palo Alto. I think it runs for another month still. It started a couple weeks ago. I would recommend doing either of those. And then next weekend is PolyCTF, which I don't remember who's running it, but that's another event. This weekend and next weekend are the only real CTFs that I know of coming up in the near future. The next one after that is like DEF CON Finals, which you already know if you're going to or not. And after that, Seesaw or something. But in any case, thanks again everybody for showing up. Hopefully it was useful, and hopefully on Monday we're able to like get some OCaml code to reproduce all of this. So thanks again for showing up, and I will see everybody in a few days. Bye.